Hello everybody. In this video we're going to continue talking about Newton, and in this time we're going to be talking about his laws of motion. Remember that Newton is obsessed with trying to understand fundamental things like what makes the Earth orbit the sun, why do the planets orbit, and why do Kepler's 3 laws of planetary motion work. But he wants to understand the nature of it. He wants to understand the physics of it. And in doing so, he comes up with humanity's first conception, the first physical laws that describe motion. And eventually, not in this video, but in the upcoming video, he comes up with humanity's first idea of this universal force that everything that has mass creates, called gravity. Let's start with the laws of motion. Yes, these are pretty heavy on the physics, but no, you do not have to run through the physics equations. I just want you to get an appreciation for what these laws of motion are. If you have already gone over the notes, this should be mostly review. And if you have watched the previous video where I talk about what motion is and what is a force, all of this is really just putting some scientific legs on all of that. Okay, so Newton's first law of motion. And this one is essentially the nature is lazy sort of law. And each one of these laws of motion, they have an associated different name with them. It's a little bit easier to remember rather than something generic like Newton's first law of motion. Well, which law is his first law? Well, it's the inertial law, which means that we need to know what inertia is. So inertia is an object's resistance to changing its motion. So it's how much does it not want to change its motion. Heavier objects are harder to push. Light objects are easier to push. Heavier objects, and whenever I say heavier, I mean more massive, sorry about that. More massive objects are harder to move. Less massive objects are easier to move. I have no problem if there was a toy pickup truck barreling down the street at me. I would have no problem sticking out my foot or just sticking out my hand and stopping that toy truck. As low mass, low inertia, I can easily change its motion from coming right at me to stopped. Now, if that was not a toy truck, but a real pickup truck barreling down at me in neutral, so it's coming at me, and what am I gonna do? Stand there and do this and stick my hand out and stop the truck? Maybe I'll try to use both hands. I'm gonna get squished. I can't stop that massive truck. Why? Because it has a lot of inertia. It has a higher mass, and it's really, really hard for me to change its motion. So it's pretty much just gonna plow right through me. All right, so now that we have an idea of what inertia is, let's actually describe the inertial law, that nature is lazy. So an object will remain at rest forever unless it's acted on by an outside force. So that's just basically saying if you have something that's sitting still, it's going to sit still forever unless a force happens to it. And remember that a force is any influence that tends to change something's motion. It also states that an object in motion will remain in constant motion. What does that mean? It means at the same velocity, so at the same speed, in the same direction, unless acted on by an outside force. So really this is saying nature is lazy. Nothing's going to change its motion unless it's forced to. And what's going to do that forcing? A force. All right, so I'm going to try to demonstrate that with some animations here. So here we have a mass, just represented by this ball here. The red arrow will be a force. And this ball would just sit here forever, not moving, zero velocity, unless some outside force acts on it. You put an outside force acting on it, and it will move away, and now will accelerate to a constant velocity. It'll accelerate until the force is over. And then it'll be at a constant velocity and move at a constant velocity forever. I go into outer space because, you know, I have a spaceship in my, just right outside here. So I could go, hop in my spaceship, go into outer space. So if I chuck this ball, then it would just move forever. If there are no other forces acting on it. Same speed, same direction. So, okay, so it'll remain at rest unless an outside force acts on it, and then it's going to have some motion, and that motion will remain the same unless a different outside force acts on it. So an object in motion will remain in the same motion unless a second force acts on it, and then it'll change its motion in response. So it's really just saying, this is nature's way of saying I'm not going to do anything unless you really force me to. And whenever you force me to, yeah, I'll change my motion. And now we get to the second law. And I know this is the same slides that I have in the Unit 1, Part 3, but I really want to talk about the rockets and the car right here. So let me go ahead and get to that in a minute, and let me introduce Newton's second law. Newton's second law of motion is the law that's going to tell us that when a force is applied to something, it's going to change its motion. That's what the first law tells us. The second law tells us how it's going to change its motion. It's going to quantify its acceleration. So given a certain amount of force applied to a certain mass, it's going to tell us how that mass will accelerate. Will it be a large acceleration, or will it be a really slow acceleration? So Newton's second law, often called the force law, is the one that tells us how a mass will change its motion, accelerate in response to a force. We can read the physics formalism of it. When a force F, so now we're giving our variables letters, so we'll call forces, we'll give them the letter F, so we can write an equation, acts on a body of mass M. See, we're pretty creative right here. Forces are F's, masses are M. It produces an acceleration, which we'll call A, equal to the force divided by the mass. So what is that telling us? It's telling us what the acceleration will be, a measurable amount. Maybe that's 10 meters per second squared, maybe that's 50 meters per second squared, maybe that's 0.0003 meters per second squared. But that's telling me the acceleration, how that object is changing its motion. And it's telling me that it's equal to how strong the force is divided by the mass. Bigger force, bigger acceleration. So if I push on something harder, I'm going to make it move more. Bigger mass for the same amount of force, slower acceleration. So back to our toy truck versus our real truck. If I have a toy truck and I push on it with some set amount of force, I can really easily move it. I can get that thing accelerating. I can get that thing really moving. I can change its motion a lot. However, pushing on a real truck, yeah, I could probably slowly push a real truck as long as it's on flat and it's in neutral. But the acceleration, how much it's going to be changing its motion over time as a function of time, is going to be really, really, really low. So this law, this force law, tells us that how an object will accelerate in response to a force. Now it's usually written as the force is equal to the mass times the acceleration, which is commonly just called F equals ma. We have that equation right here. The force equals mass times acceleration. And let's go ahead and break this down and start connecting some terms. Hopefully these bridges are slowly building in your brain so you can understand all this terminology. I just sort of talked through this, but I'll go through it a little bit again. So the acceleration that an object will experience is inversely proportional to the mass. This is my toy truck versus my real truck discussion here. So it's inversely proportional to the mass. If the mass is a lot larger, with the same amount of force, I'm going to get a smaller acceleration. If the mass is really, 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 really small, then for the same amount of force, I'll get a very, very, very large acceleration. So inversely proportional. If one goes up, the other goes down. And they do so in proportion by the same multiplicative factor. And it's directly proportional to the force exerted, which is just saying more force, more acceleration, less force, less acceleration. And now let's talk about what used to be the most ridiculous image I would show in my class: strapping a car to a rocket. Except Elon Musk goes ahead and he does it. He strapped a car to a rocket and launched it into outer space. So maybe not the most ridiculous image anymore. But here we have a rocket, and it's the exact same rocket in both of these pictures, and that's going to represent that it's the same rocket. It's going to produce the same amount of force. Whenever it fires up its engines, it'll produce the same amount of force. This rocket, we're going to strap a car to it. Good job, Elon Musk. That's you launched a car into outer space. Kind of weird, but I did enjoy the video. All right, so we have a low mass car in this case, and down here, we're going to strap a rocket to an asteroid. Also seems ridiculous until you see that NASA actually has missions to do this, or planned missions to strap rockets or really put rockets on an asteroid and attempt to redirect them so that we could take what would be a dead hit on the Earth and turn it into a near miss and thus save the world. So here we have a low mass strapped to a rocket. Here we have a high mass strapped to a rocket. The rocket produces the same amount of force. So which one do you think is going to accelerate off faster? Well, obviously this one. It's easier to move a low mass car than it is to move a giant massed asteroid. So Newton's second law, the force law, F equals ma. How a object will change its motion in response to a force. What is this acceleration given the force that's acting on it and how much mass it has? And then we have the subtlest of Newton's three laws, but also probably the most profound. Newton's third law, the reaction law. When one body exerts a force on a second body, the second body exerts a force that's equal in magnitude, just as strong, but opposite in direction. I like to call this one why you don't punch walls. Or I guess I don't have a wall I can run over and push, but let's just go ahead and whenever I hit that table, my hand hurts a little bit right now because as I hit the table, I applied a force to the table. The table applied a force that's equal in direction and opposite in magnitude into my hand. Now imagine if I were to run over to a brick wall and punch it as hard as I could. Then in that case, my hand would probably break because yes, I'm applying a force to the wall, but the wall is applying an equal force, but directed back into my hand, which is probably going to break my hand. So this is my don't go punching walls, or the subtlety of it all is why do we not fall through floors? I mean, Earth's gravity is pulling us towards the center of the Earth, right? Why am I just sitting right here still in this chair? Gravity is pulling me down. Oh, but if something's pulling me down, my butt's pushing down on this chair with a force. The chair is pushing right back up with an equal and opposite force. So they cancel out and I don't fall through this chair and through the floor and to the center of the Earth. So a subtle law. This is also the law of the basics of rocket science. How do rockets actually lift off? So here we have an old rocket with a space shuttle strapped to it. Whenever it lights its engines, there's a force from the gas being expelled this direction. So we have this downward force. And Newton's third law tells us that, well, if there's a downward force, there better be an equal and opposite upward force pushing on the rocket. And that force that's pushing upward on the rocket causes it to lift off and go to outer space. So the third law, the reaction law. For every force, there's an equal and opposite force. And finally, this is just a summary, just so we can walk through these quickly in sequence. So Newton's first law of motion, the inertial law, also the nature is lazy law. There is no motion without a force. You need a force to change motion. Newton's second law, okay, we have a force now. It's going to tell me how an object will move in response to that force. It'll actually give me the acceleration, describe how that object will change its motion, and describing how an object changes its motion is an acceleration. And then we have Newton's third law that tells us that forces are always coming in pairs. So there's always an equal and opposite force. You apply a force to one thing, that one thing will apply a force back towards you in an equal but opposite direction. So forces always come in pairs. All right, so now we are all masters on how things move. These are the three laws of motion that describe how things move. We will see you whenever we talk about a force that unlocks the solar system and allows Newton to apply these three laws of motion to understand Kepler's laws. We just need to know what the force is, and that force is going to be gravity. I will see you there.